All right, so let's look at an example of how kinetic energy becomes sound energy. We've got a collision between red and blue. Blue has a mass of 1 kilogram and is moving with 5 meters per second of velocity. Weird way to phrase that. So the cart has 12.5 joules of kinetic energy to start with. The cart also has a momentum of 5 kilograms times meters per second to begin with. When the blue cart collides with the red cart, the blue cart stops. There's a loss of kinetic energy and momentum, and the red cart goes. The red cart ends up with 2.5 joules of kinetic energy and 5 kilograms times meter per second of momentum. So momentum is conserved in this collision, right? We had 5 kilograms times meters per second before, and then 5 kilograms times meters per second after. Where did some of that kinetic energy go? Right. Missing 10 joules of kinetic energy became a sound wave, carrying the sound of the cars crashing away from the site of the collision. Anyone who's near the collision will hear a brief crash as the cars collide. But does that mean the energy is in the form of sound for only a short period of time? No. It's just when you are standing there, the sound wave is traveling away from you. So you only hear it briefly, but that sound wave will continue to move on. An example of that, when I was little, probably older than T-ball, but at the baseball fields, you'd hear another team practicing on a faraway field, and you'd see the batter take a swing, and then a couple seconds later, you would hear the ding from the bat, aluminum bats. So you saw it because light travels faster than sound, right? And then eventually you heard it. That's the sound wave making its way from the batter. To the batter, it's happening instantly, but to me, it happens a little bit later. Observers stop hearing the sound once the wave has passed, but the energy is still sound as the wave continues to spread outward. Wait, you just said that momentum was conserved because the 5 kilogram meters per second for the blue became the 5 kilograms meters per second for the red. So momentum is a form of energy. No. Momentum is totally separate from energy, and momentum is conserved under different circumstances than energy. Energy can't be momentum, and momentum can't be energy. All right, so just about finished up with this thing. Chemical energy can go directly through thermal energy, sound energy, light energy, or a combination of the 2 or 3 dissipated energies. Burning wood in a fireplace is an example of the chemical energy in the wood changing into thermal energy, light energy, and sound energy. Yes, fire makes noise. We're not going to worry too much about the chemical energy transforming directly into dissipated forms of energy. For this class, what do we care about? We care about the big one, kinetic energy. And where does it go? It goes into thermal, which we won't have to do calculations with. It goes into sound, which we're not going to do calculations with. And it goes into elastic potential energy, gravitational potential energy, and electric potential energy. The electric potential energy, not going to have to do calculations for AP. Introductory AP, anyway. Electric energy can become thermal energy, sound energy, or light energy. You got to take more physics than just this class to get to all of that. Transformations of energy other than those on the flow chart are possible, but not a focus of this course. Light can go into chemical energy, like photosynthesis. Light energy can go into electrical energy, solar panels. Thermal energy can be changed into kinetic energy, and electric energy can be changed into chemical energy. We're focusing on transformations to and from mechanical forms, as I've already mentioned. Efficiency. When energy transforms from one form to another, the energy rarely goes from 100% initial form to 100% final form. For example, when a car uses gas, only about 20% of the chemical energy in the gasoline becomes kinetic energy for the moving car. The 80% becomes thermal energy for the hot gas exhaust that comes out of the exhaust pipe. Because only 20% of the initial chemical energy became the form we wanted, we say the car is 20% efficient. Not very efficient. Another example, when a person goes upstairs, chemical energy, the calories that they've consumed, becomes gravitational potential energy. But the human body is about 10% efficient. So only 10% of the initial chemical energy becomes gravitational potential energy. The rest becomes heat in the hot, sweaty person's body. Gross. Suppose a 100 kilogram person goes up a flight of stairs, 10 meters tall. They gain a gravitational potential energy of 10,000 joules. 10% of the chemical energy used became the gravitational potential energy of 10,000 joules. This means that the chemical energy used by the person is actually about 100,000 joules. For reference, a calorie is 4,184 joules. So they burned up about 24 calories for a 220 pound person walking up a 3-story flight of stairs. That's it.